Hello folks, welcome back in this video series where we are exploring micro-segmentation in VXLAN L2VPN eVPN fabrics. In this specific video, we are going to dig into service redirection in NXOS VXLAN eVPN fabrics using GPO, which stands for Group Policy Option. But first things first, I would like to make a disclaimer. The introduction of this video is going to be a bit long. And the reason why is because I wanted to make a lot of refreshers / reminders. And you might be thinking that I'm going like too far into my back to basics approach. And actually you might be right. And to be honest, I have hesitated a lot when it came to either maintaining this refresh section or removing it or cutting it. And in the end, I decided to maintain it because I do believe that some parts of this presentation are going to be a bit complex and advanced. So I think that it is easier to be comfortable touching those concepts when we have had a refresh on the basics. So I hope that it will still be useful, and please bear with me. So with that said, let's go to this first part of the presentation, which is reminders. Now on my screen, what you can see is actually a screenshot that comes from a book. And before we go into the details of this screenshot, I would like to open the link to this book. So let me try to retrieve my arrow, which I believe is going to be a challenge as usual. Got it? Okay. So this book is actually from an author named Tony Passanen. Maybe you know him, sorry. He is a very famous engineer. He writes a lot of books, and he do maintain actively a blog. His blog's name is The Network Times. And he wrote multiple books on various technologies like VXLAN, cloud, artificial intelligence, etc. And his books are always very affordable. So as you can see, you can acquire the PDF version for a very reasonable amount of dollars. And by the way, be aware that when you buy one of his books, you are actively participating into feeding his very cute little doggy that is on the cover of all his books. Now, more seriously, you can find his book there, and you can also buy the printed version from Amazon. And I have left the name of the figure from the book so you can easily retrieve it if you get the book. So I simply changed some stuff here with another terminology that makes more sense to me, but you know that's globally it. So let's check together what we have on the slide, and for this let me retrieve my pen this time. Okay. So let's say that I have a VXLAN L2VPN eVPN fabric. For now, let's consider that it is really the classic configuration. So we are not speaking about GPO at this point in time, okay? It's very classic configuration. And let's say that I have two leaves represented here. Let's say that this is leaf 1 and this is leaf 2. Now, obviously, in the middle, I have one or more spines, but really the spines are not useful in the context of this discussion on the reminders. Okay, so let's say also that from a networking perspective, we did the configuration of one VRF, that is VRF tenant 77. As you know, for each VRF, we need to configure an L3 VNI. So we configure the L3 VNI 10,077 here. And this VRF is actually stretched on both the leaves. So we find it into my leaf 1 and leaf 2. And now I'm realizing that the leaf 1 is actually leaf 101 and leaf 2 is actually leaf 102. But okay, let's say that it is leaf 1 and leaf 2 just for simplification, okay? Now, as you know, for each VRF, when we instantiate a new VRF, what the leaf will do in the background is that it will create a table for that VRF. So it will be the ePBR table, and it will be obviously instantiated on both of my leaves, okay? Now, let's say that we are also configuring an L2 VNI inside this specific VRF, and the L2 VNI will be the L2 VNI 10,000. We are going to stretch it across both the leaves that are represented here. Again, in the background, what happens when we instantiate a new L2 VNI is that the Nexus 9K will go ahead and create a MAC VRF for that specific L2 VNI. And in this discussion, making the simplification of saying that the MAC VRF is equal to my L2 rib, okay? And the IP VRF is equal to my L3 rib. So I think you've understood it, but what I'm trying to cover and remind is all the tables that come into the picture and touch some of the processes that will be triggered when we do our learning and the propagation of the network layer reachability information from the perspective of the overlay control plane, which is BGP, L2VPN, eVPN. So coming back to our drawing, we have seen our IP VRF table or L3 rib table and the MAC VRF table or L2 rib table. Let's go further into the configuration. When we configure an L2 VNI, we map it locally to a VLAN. And as you know, in the context of a Nexus 9K fabric in VXLAN mode, the VLAN is locally significant, meaning it has a significance. I'm not sure if this word exists in English, but I hope you guessed it. Yeah, you got it. So a VLAN is locally significant per leaf. So my L2 VNI 10,000, here it is mapped to the VLAN 10, and on the other leaf, it is mapped to the VLAN 20. But what is important from the perspective of the stretching, I would say, is really the L2 VNI that is the same, obviously, on the two ends. So when we instantiate that VLAN and we do the mapping, what the switch does in the background is it creates also another table, which is the MAC address table for that specific VLAN. And the last tables that we are going to see are the ones for BGP. So obviously our control plane is, so the brain of the fabric is BGP, L2VPN, eVPN. BGP is also maintaining multiple tables, and inside each table, it has also multiple tables. So from the perspective of the quote-unquote big tables, whenever we instantiate a BGP process for a specific address family, what would happen in the background is that we are going to maintain three big tables. The first one is the local rib that is represented on both the leaves. The second table is the adjacency rib out, in which we are going to export the appropriate information from the local rib per neighbor so that we are ready to send the information present in the adjacency rib out towards the neighbors that we have inside our fabric. And the last table, it is the adjacency rib in, which on the opposite corresponds to the table in which we are going to store the information learned from our peers. In the context of this discussion, what we are going to check is the spread of a network layer reachability information from leaf 1 to leaf 2. And this is the reason why on this drawing, we are representing the adjacency rib out of leaf 1 and the adjacency rib in of leaf 2, but obviously both of them have the two tables, right? In each leaf, we have the three: local rib, adjacency rib out, and adjacency rib in. Great. And I was saying that the BGP tables are the latest ones, but actually we have also ARP table and ARP suppression cache. In the ARP table, we are maintaining the MAC to IP correspondence for the local attached host. And in the ARP suppression cache, we are maintaining the MAC to IP correspondence for the local and remote attached endpoints. So I believe we have refreshed pretty much all the tables. Now let's follow the learning of three informations. We are going to follow the learning and information propagation for the MAC of this VM that I have here. So I have VM beef here that is connected to interface 1/2 on my first leaf. We are going to follow the propagation of its MAC address, the propagation of its MAC to IP correspondence, and finally we are going to consider that we have an external router here that is connected on another port. Let's say that this is 1/10, and we have whatever routing adjacency. We can either consider that it is a static routing pointing to this router and actually pointing to this network 192.168.99.0/24. First, let's follow the propagation of the information for the MAC address. So let's say that VMbeef has been powered on and is happily discovering the network. It is sending an ARP for its default gateway. This ARP is going to reach the interface 1/2 of the first leaf. When this leaf receives that traffic, it will check the MAC address source of that's traffic. It will see also that the Ethernet header has a .1q with a tag 10, so it will understand that it is for VLAN 10, obviously. It will take that MAC address and install it into the MAC address table for VLAN 10. From there, what will happen is that we have a process that is triggered automatically, the L2 forwarder, that will take that MAC address of VLAN 10 and automatically install it into the MAC database of the MAC VRF. And yes, I forgot to refresh it, but as you know, inside each MAC VRF, we are maintaining two databases. One database for the MACs, only the MAC, and one database for the MAC to IP mapping, okay? So the MAC address will be installed into the MAC database of the MAC VRF. And from there, it will then be exported to the local RIB of BGP. Now, again, inside this table for the local RIB and the adjacency RIB out, etc., we are maintaining multiple subtables. Those subtables, that I'm calling them subtables, it's not an official term, but just to represent it and oversimplify it. Each subtable, it has the RD that represents a specific MAC VRF, IP VRF, or a specific leaf. We are not representing them here because really, for the purpose of this discussion and these reminders, it's not relevant. So we are just saying, okay, it is just the local RIB, okay? But obviously here the MAC, it is in specific RD, the prefixes will be in specific RD, but here again, we are just simplifying it, sorry. We assume that it is just the local RIB. Okay, so the MAC will make its way to the local RIB for BGP. From there, it will be processed, etc. by BGP, and it will be installed for announcement inside the adjacency RIB out. And from there, it will be announced through the spines, which are the route reflectors, to the rest of the leaves, and obviously imported only by the leaves that are interested into this learning, meaning the leaves that have the L2VNI configured. So the way that it is exported is through an announcement that we can see here, which actually corresponds to a route type 2 updates, which is an update just for the MAC. As you can see here, we have the information just for the MAC of our VM, which is BEEF. Okay, it will reach eventually leaf 2, be installed into the adjacency RIB in. From there, it is going to be processed and be finally installed into the local RIB of my leaf 2. Again, from there, it will continue its beautiful journey to be installed into the MAC database of MAC VRF inside leaf 2. And from there, it will finally go to the MAC address table of the specific VLAN that is mapped to my L2VNI. In this case, it is the MAC address table of VLAN 20. In most of the cases, the VLAN here is the same as on the first leaf, but Tony wanted to cover the most tricky use cases, I believe. So he said that this is VLAN 20. I didn't want to cover, to change it by VLAN 10 because really it's, again, just locally significant. We don't care. What matters the most is the mapping, our VNI to which VLAN it is locally mapped. So great, we have covered the NLRI propagation for our MAC address from end to end. Honestly, for the purpose of this, the rest of these slides, we don't care all about the propagation of the MAC address, but it's the easiest one to cover. And okay, so I still wanted to maintain it, but really we don't care. What we will be caring about is the next two learning and updates, which is the MAC to IP mapping and then the prefixes. For the prefix, I will be saying /24, just on simplification, but /24 equal a prefix. Obviously, it can be / whatever. So let's go to the next step. Now we are advertising the MAC to IP correspondence. So you remember everything started with our VM sending up traffic. And this time it is important that it is a kind of ARP or GARP or something like that, because previously when we were seeing and understanding the learning and the propagation of the MAC address, it didn't matter if it was ARP or something else, because for the learning, the learning of the locally attached end hosts, we are just checking the outer header source MAC address. So whatever is in the MAC header, in the MAC source field of the Ethernet header, obviously we check the .1q tag and we install it. But to learn the IP to MAC correspondence, it needs to be a kind of control plane traffic. And ARP, yes, it is a control plane traffic, okay? So when we receive this ARP on the port 1/2, we are going to check this this MAC to IP correspondence. We will first install it into our ARP table, like we do from the beginning, from the first ages of routing. But on top of that, the MAC to IP correspondence will continue its beautiful journey. It will also be installed into the MAC IP database of the MAC VRF. So inside our MAC VRF, when we check the MAC to IP database, we will see the MAC to IP correspondence for this specific VM. So that the 192.168.11.12 is mapped to this MAC address ending with beef. In parallel, the IP address will also be installed into our IPVRF as a host, so /32. This is why when we do show IP route for our specific VRF, we see the /32 entries. So when it comes to the installation into the IPVRF, the journey stops really here. We don't go further, but we still need to propagate the information to the remote leaves. This propagation happens actually thanks to the MAC IP database from the MAC VRF. From there, the information will be exported into the local RIB of BGP eVPN. And really starting from this point, we are going to follow the exact same logic, meaning that from the local RIB, we will be exporting the information, or sorry, installing the information into the adjacency RIB out of our local leaf. And from there, we are going to generate a route type 2 update that will go through the spines, which are the route reflectors, to the remote leaves. So the route type 2 update is represented here. So here we have another type 2, but on the opposite of the first that we checked previously, it's not just a MAC update, it is a MAC IP update. And here we have not only the MAC, but also the IP that is mapped to it, right? So the remote leaf will receive that MAC to IP update. It will be installed into the adjacency RIB in. From there, it will go ahead and be installed into the local RIB. And again, from there, it will make its way into two places. The MAC to IP correspondence will be installed into the MAC IP database for our specific MAC VRF or L2 RIB table. And the IP information, so really the /32, will be installed into our IP VRF table here. And the very final element that will happen is that from the MAC to IP database inside our MAC VRF, we are going to import this information to install it into the ARP suppression cache remotely. Now, obviously, all those installations happen thanks to the proper and the appropriate, imports and exports of route targets, right? But really, let's not enter into route targets for those reminders. We don't care. We don't really care about them, honestly speaking, and it would be too much details. What I have in mind is really reminding the things that will have an importance when it comes to, okay, where do GPO kicks in? Where exactly are we adding the tags and how are we propagating them? Even though we have covered most of those details in the previous videos, you know, on the ones on basic macro-segmentation, but still, it's nice to remind them, especially that we are going to introduce another type of endpoint security groups. And I really want to make the distinction between the classic ESGs, the ones that we have seen in the previous videos, and the ESG that will be used for traffic redirection. And it is just to avoid the confusions and just to help the understanding that we are refreshing those stuff, okay? So let's come back to our slide. We have finished the follow-up of the journey for the MAC to IP correspondence. The only thing that is remaining is the propagation of this, the NLRI for this subnet that we are learning through an adjacency. And let's say simply that we have a static route pointing to this subnet. So we have this static route. When we configure it, the static route will be obviously installed into our IPVRF, pointing to the proper next hop. From there, let's say that we are redistributing this subnet into BGP. So same logic as for the previous NLRI propagations. It will be installed into the local RIB for BGP. From there, you got it. It will go to the adjacency RIB out. From the adjacency RIB out, our beloved leaf1 will generate an update. This time, it's no longer a route type 2 update. It is a route type 5 update. Inside this route type 5, we will be carrying the NLRI in which we are encoding our /24 subnet, obviously with the appropriate RT and so on. So this update will be propagated thanks to the spines, which are the route reflectors. It will reach the remote leaf, and in our use case, it is leaf 2. It will be installed into the adjacency RIB in. From there, it will go to the local RIB for BGP. And from here, it will be installed into the IPVRF table. So that's it. I checked the time. I see that we have already been quite talkative, but again, I hope that you followed me till this point. I will try to speed up a bit. Okay, we have finished with the control plane reminders. So we have. This is the control plane. So this is BGP control plane. Now let's remind a bit for the data plane, but this will be very shorter. I just wanted to remind that when we do a VXLAN encapsulation, what we are actually doing is taking the original frame. So this will be exactly the same frame that the end host has sent. If we are doing switching, if you are doing routing, we are rewriting the internal MAC address. We take this original frame and we add on top of it a VXLAN header. The VXLAN header that is defined into the RFC 7348. It has actually one field that is really important. It is the VNI. So here we are encoding either our L2 VNI or our L3 VNI, depending on if we are doing routing or switching. But it's really the only field that is important. As you can see, for the rest, actually it is R, and reserved and reserved. What it means here is that those R's are zeros and they have been created for future purpose use, potential new requirements that would pop someday. And actually this is what happened with group policy option. One of those requirements actually popped. But when it comes to the original RFC for VXLAN, all those fields were set to 0 except the VNI. Then the VXLAN, on top of it, we add the UDP header, the outer IP header, which corresponds to the VTAP IP addresses, and the MAC header, which is the hop by hop MAC addresses that we are swapping when we go through the forwarding of the VXLAN packets across the fabric. Now we are going back to the more interesting stuff when it comes to GPO, which are the reminders for endpoint security groups and the vocabulary that is attached to this topic. So again, in the first two videos, we have been speaking a lot about the endpoint security group. So the ESG is the construct that will allow us to take IP addresses. And I insist on the fact that it's these IP addresses of end hosts or of subnets that we are learning. So take them and put them into a kind of container. And by container, I'm really meaning the envelope, right? It is the bag that will contain those IP addresses. Obviously, I'm not referring to Docker or Kubernetes, right? It is really a kind of box in which we are putting our IP addresses and our subnets. Each ESG would have a name so that it is easy for us to refer to it. But more importantly, it has a tag. And the tag, it is actually just a number that can be whatever from 16 to 65535, knowing that the tags from 0 to 15 are reserved and are automatically used by the Nexus 9 case for some internal purposes. So it is important to stress that the leaf responsible for assigning the tag, it is really the learning endpoint, the learning point. And actually, this is the reason why I wanted, this is one of the reasons why I wanted to make all the reminders. It's because, and maybe let me just quickly clean my screen. I hope that it won't take me too much time to find, okay, the mouse to clean all the mess. Okay, then let me retrieve back my pen. Okay, I got it. So let's say that on our two leaves, we have exactly the same kind of configuration for our endpoint security groups. Let's say that we have an ESG named servers, to which we are attaching the tag 100. Okay, and in this ESG, what we are doing is we are configuring that we are matching connected endpoints. It's actually like this inside the configuration. So connected endpoints, sorry. And let's say that the connected endpoints are into 192.168.11.0/24. So meaning the subnet that is attached to the SVI corresponding to our L2VNI. Okay. So let's say that with this, we have it exactly on the exact same configuration on both our leaves. So we configured the endpoint security group for servers, and we are going to do the same for clients. So it will be a very similar configuration. This time we are naming it client and we are assigning the tag 200. The only difference is that this time what I want to put inside this ESG is actually some hosts that come from the, let's say, external network represented by this router, okay? So for this, the syntax will be, again, pretty much the same. It's just that instead of connected, we are going to say match external subnets. And here we are going to say, okay, 192.168.99.0/24. And again, this will be present here and here from a configuration perspective. Now, who is responsible for putting our endpoints inside these two endpoint security groups? Again, knowing that the configuration is symmetric on both leaves. Now, even if the configuration is present across all the leaves of the fabric, the only leaves that are responsible for putting the end hosts inside those boxes, it is the leaves that are learning the information from the perspective of the control plane. And I hope now it starts to make sense where I spent half an hour making some refresh on back to basic stuff. Because if we go back to our VM beef that we are learning here, thanks to its ARP traffic, so control plane traffic, and when we are installing this information into the MAC IP database of the local MAC VRF and inside the IP VRF table, it is at this moment that we are adding the tag. So if we check the information, now that we did the configuration of the ESG, obviously for servers, if we check the information that is present into the MAC to IP database, we will be seeing that the 192.168.11.12, it has a tag of 100. And also, when we go ahead and do a show IP route, actually we need a detail keyword if you want to see the tag. But if we do a show IP route detail for this IP address, so the 11.12/32 inside the IP VRF, we will also see the tag there. So the tag will be visible here as well, the tag 100. And obviously, when we do all the exports, we are going to maintain the tag attached, right? So it means that when we do this export and then go to the adjacency rib out and generate the updates through this route type 2 here, we will actually put the tag. So it will be added there. thanks to an external community. Actually, the theory is a bit lower in the slide that we are checking right before coming back to this one. So we didn't see the refresh the theory yet, but never mind. Let's still touch it a bit here. So here we are going to add the tag in the form of an external community in the BGP update. And also, something important that we mentioned into the two previous videos, the tag is really added here, not on the MAC update, because again, we are only matching on IP addresses. It's the IP addresses of the host and the subnets that we are adding into ESGs and that we are advertising, and for which we are advertising this mapping information between the endpoint and the tag through the update. So it is really inside the MAC to IP route type 2 update that we will be adding the tag. Now, obviously you got it, the update will travel, etc. And in the end, when we will be installing the MAC to IP correspondence there, actually we will be adding the tag. And I'm just checking the video because I feel like it's freezing a bit. I hope it's not. I will have the surprise at the edition. So crossing fingers. Okay, so here we will have the tag 100 visible, and here as well, when we do a show IP route, we will see the tag 100. Exact same thing goes for the learning of the subnet, because here we are learning it through a control plane as well. So even if it is static routing is still a control plane. Obviously, if you do OSPF, whatever, since we have the match of this subnet, when we install the route there, we will be adding the appropriate tag, which is 200 for our use case. So here we have tag 200. And then exactly the same happens. So when we will install the route into the local RIB, then generate a type 5 update, this update, we will be adding the tag 200. Thanks to the same extended community, so that when the remote leaf receives this update and when it installs the prefix, and sorry, apologies, I realized that the tag 100, I positioned it into the wrong place. So the tag 100, it was for the host. Sorry about that. Okay. This is for the prefix. So here we will have our tag 200. I was so focused on the video that was seeming to be freezing, like Elsa, that I put the tag in the wrong place. So tag 100 is for the /32 because it was for the servers, and the tag 200, it was for my prefix. It's my clients. And if you wonder what happens when we do a more wide matching, like for example, let's say that in the external subnet, we didn't configure 192.168.99. I don't know, let's say that we configured a 192, 168, or even 1.0/16. Then in that case, this subnet would still be tagged because it is contained. It's really intuitive, right? It's contained there. If we configure a shorter prefix, then in that case, it won't be matched. For example, if we do 192.168.128/25, then in that case, we are not containing this subnet, so it means that we will not be assigning the tag to it. Okay, so I really wanted to stress about this thing that we are assigning the tag at the entry point, and then we are propagating it through the fabric thanks to our route type 2, MAC to IP updates, and our route type 5's prefix updates. So both of those contains our tags. And if we check the appropriate RFC, so I'm not going to click on the links, etc., because this we did in the last video. I just wanted to remind that it is through an extended community. So it was a new RFC that has been published, or I believe it is a draft, but whatever, it is something official that has been published to announce this extension. So we are creating another extended community in which we are coding the tag. And again, as usual in networking, we have plenty of names to designate the same thing. The group policy ID is actually what is referring to our tag. So here we will be transporting the 100 or our 200. So this is from the control plane perspective. Now, if we go back now to the data plane perspective, because we need to touch this as well, right? So what the community of brilliant engineers did to carry the information of the tag, and by the way, I want to insist on something. Into the VXLAN header, we will be carrying the information only of the source, right? There is a field that will be used among those reserved bits of the original VXLAN header that are being used now to encode the tag of the source of the traffic. So the source, the tag of the source of the traffic is the SGT, so source group tag. Let's say like this. So what does it look like? It looks like this frame, this header. So you recognize the VNI that we were mentioning in the previous slides. And now inside the header, we have this group policy ID that is being encoded. Fortunately, sorry, let me remove my face. Fortunately, it has the same name in both the extension, the new RFCs. So for the control plane and the data plane, they kept the same name. So we have some consistency. It's the group policy ID. And we have then also two important bits that are being used. It is the G bit and the A bit. So if we oversimplify, we can say that if the G bit is equal to 0, then we are in the context of the original VXLAN header, meaning the VXLAN header that does not include the support for group policy option. So if G equals 0, the only field that is important and that is relevant is really just the VNI. Now, if G equals 1, it means that we are in the context of this VXLAN group-based policy extension. And it means that we are carrying information regarding the group policy. At least we have the group policy ID. Sorry, I wanted to highlight it and then I ended up removing it. So we have the group policy ID, which is the source tag that is encoded. So the source tag. And we need to pay attention to this A bit. So if G equals 0, then we need to pay attention to the A bit. The A bit can take two values. Sorry, if G equals 1, apologies. If G equals 1, we need to pay attention to the A bit. If G equals 1, the A bit can still be equal to 0 or to 1. What is the purpose of this bit? The purpose of this bit is for the leaf that is creating this VXLAN encapsulated packet to tell the remote leaves if they still need to apply some policy or not. Actually, let me rephrase. When we have group policy option, obviously we are going to define some policies across the leaves. The source leaf will apply or not a policy. So the source leaf will apply a policy actually. When it applies a policy, normally it should say always A equals 1, right? Because it has applied the policy. So if we consider our simple example there, and we are doing some policy, whatever it is, it can be a deny of something, or redirect, not deny, but a redirect or something, we should say, okay, we have applied the policy and we should position the A to 1, right? So you might be wondering, what's the use case of having A to 0? Actually, we can still position A to 0 even if we apply the policy, just to force the remote leaves that are going to receive that traffic to reapply a policy. Because the thing is that if the leaf 1 puts the policy at 1, then the remote leaf will do nothing. If we want to force the remote leaf to apply some policy, then we need to say to put this bit to 0, so that the remote leaf will say, okay, no policy has been applied, I need to reapply a policy. If you think what are the use cases where we want to quote unquote trick the remote leaf, we are going to explore them into the redirection, but that's the idea. So let me go back to this slide, and I believe we covered everything. So let me just quickly clear this mess and take back the recording. So let's go to the next slides and remind ourselves of the main use cases for GPO or group policy option. So we touched a bit this one, the creation of security zones, in the previous videos. Actually, we did more than touching it a bit because we even did a lab on that, right? We created two security groups. It was clients and servers. and we permitted some of this traffic and we denied the rest of the traffic, obviously in the same VRF. So we did a demonstration of these capabilities. It's very nice to say that inside the same VRF, we can enforce some security without needing any kind of external device, any kind of firewall. So we create just two endpoint security groups, so 1 and 2, and we say whatever traffic we want to permit and whatever traffic we want to deny, just by creating class maps and policy maps. For the constructs, we are going to refresh them as well when it comes to the class maps and the policy maps, because when it comes to traffic redirection, we obviously need them, and we even need additional stuff, which is very funny. So let's go back to our slides. I'm trying to find the right position for my face so that I don't cover what's written. So this was the first use case. And again, if you want to refresh your ideas on this, I would encourage you to check out my first two videos. I need to learn how the YouTubers do to say, okay, the video will be attached there or there. But by the way, it's never at the place where they are pointing, which is also very funny. Okay, sorry, never mind. More seriously, the second use case, which is going to occupy us a lot inside this video, is the service chaining. So what ESG allows us to do is give us a lot of flexibility in order to say that, okay, for my ESG 1 to my ESG 2, I don't want to just permit the traffic. I want to permit the traffic, but first make it cross some device in the middle before sending it to the destination. Now, what this device is, it can be really anything. Usually it will be a security device, right? Or load balancing device. But in the rest of our discussions, we will be considering, just for the sake of illustration, we will be considering firewalls and intrusion detection systems, again, just to represent the logic of it, but it can be anything. So the global idea is that we are taking our endpoint security groups and redirecting the traffic through some additional device before allowing it. Now, obviously, we can say that from this ESG to this ESG, some traffic is denied. For example, we say telnet is always denied. We can say this. And we can say also that HTTPS is allowed, but only through this device. And we can even have the flexibility to say, okay, ping is simply allowed. So for the ping, we can simply do this. Okay, so we do not do any kind of redirection. So we have all this flexibility. And speaking of flexibility and so on, I would like to use this drawing to introduce or remind some key terminology points again. So let's consider this use case where I have a fabric that consists into 4 leaves, so leaf 1, leaf 2, leaf 3, leaf 4, and 2 spines. On these 4 leaves, I have some endpoints that are attached. So I have a VM source here, a VM destination, I have a firewall, and I have an intrusion detection system. So let's check out these terminology elements. When we will be speaking about forward traffic, we will have in mind the traffic from the source to the destination. So this will be our forward traffic. Now, you guessed it, I believe the reverse or return traffic will be what we will have in mind when we speak about the traffic from the destination to the source. Okay, so this is what we have in mind with forward and reverse or return traffic that we will be using. So reverse and return, we will be using them interchangeably. So the third definition that I want to highlight is the redirection or steering. So again, these two words, we can use them interchangeably. We can find the two into the documentation. What it means is simply to say, okay, instead of simply allowing the traffic, as we were mentioning in the previous slide, we want to steer it through some specific devices before allowing it to the destination. So here we are first making it through the firewall, then through the IDS, then allowing it to the destination. Now, before we go to the next definitions, I want to again clear the mess on the screen. Okay, good. So let's spend some time into exploring the definition of service and service endpoint, because it might sound obvious, but when it comes to the configuration that we are going to do on the leaves, because we are going to explicitly mention service in the configuration, service and service endpoint actually as well. So we need to clarify what is behind those terms from the perspective of the Nexus 9K and also from the perspective of the configuration. So, and for this, let's just consider the firewalls first, knowing that exact same stuff will apply to the IDS. A service can be, for example, a firewalling service. So let's say that my first service is firewalling. So in my configuration, I will be defining a service named firewalling. Inside this service, I can define one or multiple service endpoints. For example, let's say that we are going to define 3 service endpoints: firewall 1, firewall 2, and firewall 3. Now, a big important stuff. Each of these firewall is referred to by its IP address. For example, 192.168.101.1. Let's say 192.168.101.2, and let's say 192.168.201.1. So each of these firewalls has its own IP address, obviously its own MAC address. It means that I'm considering 3 active service endpoints. It's not a use case of active standby. Now, in the background, each of these firewalls can be itself a cluster of active standby. So it means that, for example, in the background, I can have that my firewall 2 is actually a cluster of an active and a standby. So this is a standby. I think you got it, but I've never been talented into drawing. This is why I did an engineering career. No, more seriously. So firewall 2 is, it can be a cluster of active standby, but from the perspective of the service that we are considering, we are mentioning 3 active firewalls. Now, I believe that you are starting to see the challenges, right? Because what we always fear when we speak about active security devices is the drop that we can have if we do not have exactly symmetric reverse traffic, right? So it's nice to have these beautiful active endpoints that are independent because we can do load balancing between them. We can share the load so everyone works and handle a part of the traffic. But it works only if you are able to ensure that the return traffic crosses exactly the same service endpoints that the forward traffic has crossed, right? And actually, the solution of ePBR, extended policy-based routing, allows this. We are going to see the details of how it does, but it allows it, and it's actually one of the beautiful things of the solution. So that's a generic ID for the service and the service endpoints. So again, one service endpoint equals one IP address. Now, on my drawing here, I have just one service endpoint for my service firewalling, but I could have 3 or more. It doesn't matter. I can have as many as I want in a specific limit that I don't have in mind, obviously, but that's the idea. We can configure multiple ones. And we can configure also a service named IDS. For example, I could have a service IDS that consists into 2 endpoints. So IDS 1 and IDS 2. This will allow us to go to the next 2 important points: monitoring, probing, and load balancing. So monitoring, probing, I guess it is self-explanatory. We want a solution that allows us to dynamically check if our service endpoints are alive. And if they are not, just to kick them out of the picture so we don't redirect traffic to a dead end, right? So the probing can be something very simple, such as doing some regular pings, or it can be more complex, like checking if we can retrieve a file or checking if a specific port if the end device is listening on a specific port. So we can be quite creative with this probing, and we can use the results to say, okay, we can maintain the endpoints inside the service or we remove it. And by the way, when we consider the ePBR in the context of GPO, and this we are going to see more in detail later, but just as a spoiler, we can even go into more fancy stuff, like saying, okay, I want to actually do something on my service even if all my endpoints are not dead. Let me rephrase. What we see is that in a specific service, we can have multiple endpoints, right? If one of my endpoints no longer answers to the pings or to the probes, we remove it. But the rest of the two services are still available, so we can send traffic towards them. What we can do also is define a threshold below which we say, okay, even if I still have endpoints inside my service, I do not want to consider anymore this service. And in that case, we can have multiple actions that we can take. For example, we can say, okay, if my service is no longer available, I want to drop the traffic. I want to be very drastic and drop the traffic because this service is really important. If I consider that I'm too low in number so I can have a bottleneck, never mind, I decide to drop the traffic. On the opposite, if it was a service for, I don't know, some optimization, I can say, okay, if I'm below a threshold, this time I will just bypass and just say that I'm not considering this service anymore, but check the next services. Okay, so we have these different kinds of actions. And I believe this will not be checking this with this video, but in the next one about the fancy stuff about the redirection. And the load balancing, we actually touched it a bit in the global explanations. So the idea is that we are sending traffic to multiple endpoints of the service. And the way we do it is through hash. So I think you guessed it. We are going to do hashing on things that we can specify into the configuration. It's, as most of the times in networking, we can say just the IP source, IP destination of the traffic, or we can even consider the transport protocol, TCP or UDP, and the ports that are in the layer 4 header to do this hashing. And we ensure that the result of the hashing for the forward flow is the same as of the return flow in the way that the algorithm is built. So let me just touch quickly symmetry before we do the service chaining, but symmetry, we already mentioned it. So what we want to do is that if the traffic from A to B, let me draw B here. If this traffic on a specific, obviously for the IP address of B, but let's say it's TCP traffic for port 443, let's say it is hashed to the firewall 2 and to the IDS1, we want to ensure that the return traffic goes to the IDS1, then to the firewall 2, then to A. So that is the symmetry. And finally, service chaining. So the chaining is simply, it's actually a quite self-explanatory name. It means that we are taking two services and put them, two or more services and put them into sequences. For example, let's say that the sequence 10 would be service firewalling and the sequence 20 would be the service IDS. So that's it for the global terminology points. I really wanted to make a slide on them because we are going to speak a lot about all these key points as we are going to move on. So with that said, let's put some perspective into all this. Let me remove my face. I believe here is okay. Great. So I'm not hiding any writing. Oh, so just some background on the slide that I'm showing on the screen. Actually, when I was preparing the slides for this presentation, I wanted to include first some slides about PBR, so policy-based routing, then add some slides on ePBR, so enhanced policy-based routing. So I think I said extended policy-based routing, it's enhanced policy-based routing, ePBR. To finally reach the ePBR with GPO, so group policy option. And then I realized that the deck was too big, even for me, and I know that I'm talkative, and I think you know it as well, right? Even for me, it was too long. So what I did is remove the parts of PBR and ePBR, and I put them into another deck. So the deck is ready. I just need some time to record it, but the deck is ready, and I believe it is interesting to go through it. And instead of having all those slides inside this presentation, I just collapsed everything into one slide because, in my humble opinion, it is still important to have in mind the background and how we reached the ePBR with GPO. So actually, it all started with PBR. So policy-based routing, which we also already spoke a lot about it into this presentation, but from the perspective of, our experience with PBR, I believe that every network engineer has configured PBR at least once in his life, even on iOS devices, because some use cases happen when we are into the same VRF and we do not want to allow direct communication between two subnets. We want to first redirect it to a firewall. So it is very simple use cases, right, where we are defining a subnet source, a subnet destination, and we are just defining one endpoint that needs to be crossed, one firewall, and that's it. Not multiple services, not multiple service endpoints for that service, just one endpoint that we are signaling. So very, very simple policy-based routing. So this very simple PBR, it is actually supported into VXLAN, but again, it has a lot of limitations and it's really done for simple traffic redirection use cases. So if we just need to do something as simple as I was mentioning, so two subnets and one endpoint that we are crossing in the middle, PBR makes sense. If you want to go more fancy and introduce all the features that we are speaking about into the previous slide, then we need something more strong and powerful, and that strongness and powerfulness has been introduced by the enhanced PBR or ePBR. So let's go through these two paragraphs that I took from the configuration guides, which summarize really nicely what it does. So it provides a comprehensive solution to insert service nodes, selectively redirect and load balance traffic. So ePBR provides a simplified workflow to create traffic chains and load balancing rules, along with providing options for probing, monitoring the health of service appliances, and taking corrective action in the event of failure. So this small paragraph actually refers to all the stuff we were discussing into the previous slide. So again, all these features have been introduced by ePBR. And also what is interesting is that it automatically creates multiple PBR policies and apply them on the service interfaces belonging to the service nodes. Let's check out in more details what this means. So let's see, for example, this drawing. Here I have, again, a beloved fabric. I have some traffic that is coming from the WAN, and it needs to reach my host B here, that it is in VLAN 20, okay? For this traffic to be allowed, I want to first redirect it to a service firewall, which has two endpoints, and a service, let's say IDS again, which has also two endpoints. So the traffic will go, let's say, for example, first to the firewall 1, then to the IDS 2, then go to the destination. This is what we said, service chaining with redirection with service chaining. Now, from a configuration perspective, and this is what we will be touching extensively into the slides on ePBR, we need to configure the policies that, you know, do the magic, right? It doesn't happen out of nowhere. We need to configure the interface that connects to the WAN, saying that we want to apply a policy here. And we need also to configure some stuff on the layer 3 SVI interfaces that are on the leaves, and also on the interfaces that connect the to the service endpoints, so that we say, okay, when the traffic comes back, I still want to match it to redirect it to the second service endpoints and so on. So actually it can be quite a long configuration, but what ePBR workflow allows to do is take some of the burden of this configuration and automate it in the background. Even if we are not using, a controller, even if we are not using NDFC, this is really when we go into the CLI and we push the configuration, there is a lot of stuff that is pushed automatically into the background. For example, when we configure the ACL for the forward traffic, and we apply the proper policy on the incoming interfaces, what will happen is that ePBR will take the burden of configuring for the reverse traffic, the ACLs, so automatically. Okay, so again, key takeaway: it is ePBR that brings the enhancements that we have touched into the previous slides. Now, what SGACL, Enhanced Policy-Based Routing, or ePBR with GPO will do is take this ePBR and combine it with GPO. So you can find the two nomination into the documentation, either SGACL, sorry, I lost my pen, either SGACL ePBR, meaning that the ACLs that we are configuring are no longer ACLs that are matching subnets. It is ACLs that are matching endpoint security groups. So hence the name SGACLs. Or ePBR with GPO, because again, GPO is group policy option. In whatever terminology the key takeaway is that we are referring to the fact that we are using groups, right? So the G is the master here. G is the new black. So this is what we will explore. So we are, and I believe that I took a very fancy slide, not a straightforward slide actually, but to say this in a fancy way. So we are actually combining the classification enforcement capabilities of micro-segmentation through those SGACLs and the constructs of service chaining through ePBR. So the sum of the two gives us this great SGACL ePBR. It's like we were taking Goku and Vegeta and make Gogeta. If you are too young to understand, I believe I'm even older than what I thought. Okay, sorry, more seriously. So we are taking these two constructs to build SGACL ePBR. So not only we are classifying the inter-application traffic more granularly thanks to these groups, but we can define very granular and precise rules and go very creative into those rules to redirect the traffic through services that we have in the network, such as our firewalls, IDS, traffic optimizer, TCP optimizer, IPS, whatever, we can redirect through anything. Actually, into our lab, all those fancy devices to which we are redirecting traffic, it's actually just IP addresses of a Nexus 9K that will simulate all this stuff, but that's the idea, we can redirect to anything. Okay, so let's see from the support perspective. So this support has been introduced into 10.4.3. So starting from 10.4.3, we can do the ePBR with micro-segmentation, because ePBR has been supported before. I believe it was into the introduction has been done into the 9.3 train, not 100% sure, but ePBR with micro-segmentation, it has been introduced into 10.4.3. And by the way, all those devices can be either dual ARM or one ARM. We really don't care. Just from the configuration perspective, if we have multiple ARMs, we have something to do to add in the configuration. But from the logical perspective, it really doesn't matter. So again, traffic will be redirected and load balanced to devices inside the cluster before being allowed to travel to its destination. So this we mentioned a lot, but what I would like to highlight is that for the rest of the conversation, just to simplify the stuff, when we say service redirection, we will have in mind also load balancing, if applicable. Obviously, if you have just one device into the service, it doesn't make sense to load balance. But if you have multiple devices into our service, so multiple service endpoints into our service, when we are redirecting through this service, we are automatically load balancing between the service endpoints. Actually, we don't even have to do anything. We just need to give the algorithm, so the IP source, IP destination, layer 4, and the ports, if you want to take them into account for the hashing. But once we have done this, when we redirect to the service, we are going to automatically load balance between the service endpoints of this service. So when we say redirection, load balancing happens in the background automatically. So we can say that redirection and load balancing is the same stuff. Obviously, it's load balancing between the endpoints of the service. We are not considering the load balancer service. A load balancer as a service endpoint. It can be a service endpoints, obviously, if you have a load balancing service, but here it is load balancing between the endpoints of a service, whatever the service is. Okay, and finally, stuff that I want to mention is that into the release 10.4.3, the service chaining is not supported with ePBR micro-seg. So honestly, I didn't check the latest release notes for the 10.5 train. Maybe they have been, the support has been introduced, but just be aware that when the feature for SGACL ePBR has been introduced, service chaining was not there. So it means that if we take back our slide where we were representing the chaining, in 10.4.3, we cannot have the IDS here. We are still going to configure the constructs chaining, and it's actually one of the reasons why I still wanted to touch it. But our chaining will have just one sequence number going to just one service. Now, the service can still contain multiple endpoints, but we still have just one service. In future releases, we will be able to configure the additional sequences with the additional services. But for now, this is what we have. Okay, now let's see just some more generic considerations, but I believe we have already covered a lot of these terminologies. So here we are considering a fabric with one service that is named, let's say it's service firewalling. This time it consists into 4 endpoints. So what I want to stress, even if it's obvious, is that really the services can be connected anywhere in the fabric, and they have multiple types of connectivity. Here, for example, is through a VPCPO. Here is through just a single interface. We really don't care. From the logical perspective, it is the same. And what I want to highlight also that we didn't touch yet, it's that there is no notion of affinity. What it means is that when we consider, for example, traffic from host A to host C, we can really pick any of those firewalls. There is no kind of priority given to, for example, firewall 1 because it is connected to the same leaf as host A. Because again, the hashing algorithm, what it takes into account is the header of the flow from host A to host C. Sorry, from host A to host C. We are not checking where the firewalls are physically connected. And it would not make sense anyway because they can move if it is VMs, etc. But that's the idea. There is no notion of affinity. The only thing that matters, again, is that we pick the same firewall for the return traffic as for the forward traffic. So here we picked the firewall 3 for the forward traffic. So the return traffic also picks the same firewall. So this is what I summarized there, that we have no affinity, meaning that no preference is given to local firewalls over remote firewalls. The algorithm, what it takes into account, it is the source destination IP protocol. We can just have the source destination IP. We specify the load balancing algorithm, like in most things in networking, but that's the idea. This is what we take into account. And again, a very last time to say this, because it's, again, a really important concept, is that the ePBR services, they represent cluster of destinations. We can have multiple endpoints and each of the endpoints be a cluster of active standby. It can happen if we want, but it is multiple service endpoints and each one is defined with its IP address. And this IP address is very important, obviously, to find the service to which we want to redirect the traffic. So find it where it is attached, and also to send the probes so that we can monitor if the service is properly alive or not. Good. Now we are going to move to a very important slide in which we will be trying to recap all the constructs that we need from a configuration perspective. So in this video, we are going to explore this slide like step by step with all the constructs. And in the next video, what I did is take back that same slide. I mean, next video where we are going to do some lab. So I will take that same slide and put the name of the constructs that we will be creating so that it makes sense and we can see very clearly how all the pieces of the puzzle fit together. So let me position myself there. I'm not hiding anything. Good. So let's check this slide column by column. First, we mentioned it multiple times. We have our ePBR service. So a service is a collection of service endpoints. For example, the service firewalling that we have been speaking about a lot. We have, for example, firewall 1 here and firewall 2 here. And the service, let's say that the service IDS, it has an endpoint IDS1 and an endpoint IDS2. So this is the very first thing that we need to do, create the ePBR services and the service endpoints with their IP addresses. Once we have done this, we can go ahead and create the ePBR service chain, which is an ordered sequences referring to those ePBR services. Again, in 10.4.3, the service chain can contain only one sequence, so we cannot put the firewalling and IDS one after the other if we are using GPO. If we are using classic ACLs, I mean IP ACLs, we can do this chaining. But for ePBR with the group policy option, so with SGACLs, we cannot do this. But still, that's the global ID. We create the chain and we refer the different services. So that's it for the first column. Now let's go to the second column. And This we have seen extensively in the previous 2 videos on basic micro-segmentation. We are creating some security class maps. So when we create the class maps, we enter the keyword security, where we are going to do some filtering. So here we are going to do some match filtering. For example, we can create a class map security type security that's named SSH, on which we are matching the traffic towards port 22. Then we can create a class map that we can name telnet ICMP, where we are matching ICMP and destination towards TCP23. So we have created these 2 class maps. And something important that I want to highlight is that really at this step, we are just creating the, how can I say, so let's say quote unquote, the pattern of the traffic. What I mean by this is that we are not specifying who is the source, who is the destination. It is just an absolute. It is ICMP. It is traffic towards port 22, towards 23. Really, it's just a generic class map. So it is really just to say, to identify the kind of traffic that we are referring to. Okay. It is at a later step that we are going to say specifically from which to which with that filter we are matching. For now, it's really just, again, I don't find another word than absolute type of traffic, a kind of pattern. I'm not sure if it's appropriate, but I think that you got the idea. So once we have done these steps, we can go ahead and create a security policy map. Now, the security policy map, it will leverage these 2 constructs. So it will say that when we are matching the criteria referred to the class maps, then we do some action. For example, in our security policy map, we can say, okay, for this class map, ICMP telnet, what I want to do is simply permit, meaning we are going to do the forwarding based on the classic IP routing of the VRF. No additional action is needed. Then we are going to create another entry into the policy map to say, okay, if we are matching the class map SSH, in that case, we want to go steer it through a service chain. So the service chain being this one that we have defined there, obviously, right? And finally, we can either create another class map saying, I don't know, HTTP, so towards 80, and say, okay, if we are matching this class map, then I want to deny. So this is what we are doing with the security policy map. But again, even here, actually, we are not referring explicitly to any source or destination. We are still referring to this filtering and specifying an action permit, deny, or redirect to our service chain. But it's still applying on traffic patterns. So it means that we need to go further steps to define the sources and destinations. And this is what we are actually going to do with actually this column, the pink one. So this pink is divided into two parts. One that we touched into the previous video and one that is brand new. So the one that we already touched, it is this one. We are matching some selectors and putting the hosts, matching these selectors into specific endpoint security groups. So this is what we did when we were referred into the beginning to saying, okay, we are putting 192.168.10.0 into the ESG client, which has a tag of 100, and 192.168.20 into the ESG servers, which has a tag of 200. I'm not sure that it was this subnet that we used in the beginning, but it really doesn't matter. I think you got the ID. And two things. If you want to have more details on this assignment, I would, again, highly recommend to check the previous videos or at least the lab so that you can see how they are matched. And the second thing is, if we go back to the very first slides where we are doing the reminders of how everything fits together from the perspective of the control plane. So what we are referring to, it's really the example that we did here of assigning the tags from the learning from a control plane. And this is actually the main reason why I wanted to spend that much time on that, to make the difference between the two columns for the endpoint security group. So now we are checking the left part. So the one for the classic ESGs, clients and servers. For these, we can actually either match, it can be connected or external, it doesn't matter. It's just that it is the endpoints that we are putting thanks to the control plane, whether it is ARP initially that generated the learning or it is a routing towards an external destination, it doesn't matter. It's really from the control plane that we are learning the endpoints and that we are putting them into ESGs, and then we are propagating this mapping between the endpoints and the tag across the fabric thanks to BGP eVPN. So everything starts with a learning from a control plane. And I'm sure that you see me coming. The reason why I stress this is because the next type of ESG we are going to see is not a learning from a control plane. It is actually what we call the layer 4, layer 7 ESG. So it is a very specific type of endpoint security group. It means that inside the configuration itself, we are going to refer to the keyword layer 4, layer 7. I don't remember if it is layer 4, layer 7 or just L4, L7, but we are going to refer to it as being a layer 4, layer 7 ESG. And for that one, we are not learning into the control plane. We are matching what is being named here an interface selector. What it means is that if we consider our drawing here, and let's say that this is a firewall that is connected to the SVI, let's say as VLAN interface 1001, what we are going to say is explicitly inside the configuration, match interface VLAN 1001. And everything that is coming from this interface into the data plane will be classified through the data plane inside that ESG. We are not doing any learning from the control plane perspective for that ESG 1001 with the default configuration, and this is what we are going to use. I don't remember the beginning of the sentence, but what I mean is that we are not doing any kind of learning inside the control plane. When we receive traffic from the firewall through this interface, all that traffic will be positioned into the ESG 1001. And I believe that you are starting seeing the, not the challenges, but the main things that we are going to explore into the next slides, because we have seen in the previous slides that we transport the information of the source group inside the VXLAN header, right? And now I'm telling you that we are introducing another tag in between. So how does everything fit together? Actually, what we are going to see is that at some point in time, inside that traffic flow, we are going to do what is called the swapping of the ESGs, meaning that when the traffic is sourced from this endpoint, it will have the tag 100 that we see here. It's very small, but I hope it's readable. It will be redirected to the firewall and come back through the interface 1001. Thanks to the configuration that is matching the interface selector, we are going to put this traffic this time into this additional ESG, which will be, for example, 500. So it means that the traffic that will then be sourced from this leaf will carry now the tag 500. It no longer carries the tag 100. All this, I will explain it into details. I'm just checking the time because I'm seeing that the video is already very long and we have a lot of things to cover, still have a lot of things to cover, but never mind. I'm trying to make things clear. I just hope that by repeating things, I'm not adding more confusion, but okay. So we are going to dig into more details into this swapping of ESGs. So now we are ready because with all this stuff, we have all our constructs to go ahead and apply our contracts. So you remember I said multiple times that at this step, we are not referring to any explicit source or destination. We are just referring to a kind of traffic. So towards port 80, towards port 22, never mind, and applying an action on it. But now we are saying, okay, it's not just any kind of traffic. It is from a specific source ESG to a specific destination ESG, we are applying a policy map. So it means that, now I think it's simple now, right? It means that if we take our security policy maps, it is from our ESG clients to our ESG servers. If it is port 22, we are doing, it was service chaining, I believe, that we mentioned into the example. If we are doing Telnet or ICMP, we simply permit. And if you are doing 2080, we are dropping. I honestly don't remember, but that's the generic ID. It's the security contract, and actually it's something that we apply at the VRF level. The security contract is what allows us to put the glue into all the pieces of the puzzle and say, what is the ESG source, what is the ESG destination, and what kind of action we want to do inside of it. So when we go at the VRF level, we mentioned that in the VRF level, we don't refer to the ESG of the firewall, so the layer 4, layer 7. This is referred in another place when we configure the service chain and the endpoints and so on. Not inside the VRF, but because inside the VRF, what matters is just the source, the destination, and the action. So that's it. This was a very important slide in my humble opinion. So now let's dig more into the layer 4, layer 7. So this ESG, again, it's specific ESG that has been created to facilitate the service redirection. So again, as mentioned, we are going to say that it is a specific type of ESG thanks to the configuration, and we are matching on a logical interface. So this is what will be the matching criteria. So if you remember from the first slides when we were doing the positioning of the endpoints inside the classic ESGs, we were matching on connected endpoints or external subnets, but in any case, it was matching on IP addresses. Here we are matching on an interface, saying all the traffic coming from a specific interface will be put inside this ESG. And again, it's from a data plane perspective, not a control plane perspective, like the classic ESGs. So by the way, for the moment, only SVIs can be selected and the priority is 0. It means that really when we match something from there, but this we are enter into more details later, is the idea of priorities between the ESGs. If we have multiple things that kind of overlap, this one has a higher priority. It means when we come from this interface, and if we have a configuration that say, okay, match this interface, put into the L4, L7 ESG, everything will be put there. It is what has the higher priority. Okay, so before we go to more interesting stuff on how happens I was going to say label swapping. No, the swapping of groups inside the headers, just final considerations. So for the fail actions, but I believe you have already touched most of it inside in the global discussions of previous slides. We can specifically tell the device what actions we want to enforce in case of failure. So it can be again, for the failures, it can be just considering the failure of one device. For example, if we take back our use case of having 3 firewalls, we monitor the 3 of them. Let's say, for example, if firewall 3 has failed, we still want to consider our service and redirect and load balance to firewall 1 and firewall 2. But we can also be more creative and say, okay, if below one threshold, so for example, if I lose 2/3 of my available endpoints, then I want to consider the service as failed. So here, even though I have firewall 1 that is still alive, I have lost 2 and 3, so I can tell the configuration, okay, it's too much to have lost 2 and 3. Let's consider that the whole service has failed. And also, when we have defined those criteria, we can also say what we want to do, which can be dropping the traffic, which is very drastic, or forward traffic bypassing the ePBR service if it has failed. What it means here is that, for example, let's say that we have a sequence, a chain of 3 sequences. Again, this is not supported yet with SGACL ePBR, but it is with classic ePBR. If I lost my first sequence, I can say, okay, just bypass it, so consider the other 2 sequences. Now, from hardware and software requirements, the support is the same as for SGACL, so it means that we need FX3 and newer. And something important is that you always need to be careful when we say this is supported and on this device or not. I mean, when I say we, it means me as an individual, not as a member of a specific company, right? This can change, obviously. So because usually what happens is when a new feature is introduced, it's introduced in the latest hardware. And in most cases, it is backported into a bit older hardware. So this means that depending on when you are checking the video, it can change. So I will not come back to the video to say, okay, it's now supported on FX2, right? At the moment, we are into December 2024. It is supported on FX3 and newer. Now, how do we are able to configure everything that is related to SGACL? The first thing that we are going to need is feature security group. Now, in the previous two videos, we go in all the teeny details to be able to enable feature security groups because it has some dependencies. It actually has a big dependency on the template that we are using because it requires the template security group to be configured. And when we change to this template, we need to reboot the switch. And this template itself, it requires an SSD repartition. So what we can do is configure the template and then do the SSD repartition, which triggers automatically the reboot. So when the reboot is done, we are ready to go. We have the repartition and the template is enabled. Again, if you want to see more details, you can check the previous video with the lab environment. So once we have done this, we can go ahead and enable our feature security group. Obviously, we need to enable the feature ePBR as well because we are doing ePBR with GPO. And last, if we want to do some dynamic probing, we need to enable the feature SLA. Otherwise, we do not need it. Okay, so now we are going to check the last part of this presentation, which is the data path with the SGACL-based ePBR. So for this, we are going to consider this drawing that we have already seen in the previous slides. So we have two VMs, 10.10.10.10 and 20.20.20. And we have a firewall and an IDS in the middle. Now, again, and I believe I'm saying again 10,000 times into this presentation, this is not supported yet. So meaning the chaining, we cannot do it yet, but the global ID is still the same. So what happens first? So first, these two VMs will start sending ARP traffic or control plane traffic. The leaves will this will allow the leaves to put the VMs into the proper ESGs. Sorry, into the proper ESG. So thanks to that, leaf 1 will put 10.10.10.10 into the ESG 55, and it will put leaf 4 will put 20.20.20.20 into the ESG 56. We spent a lot of time to explain then that when this is done, leaf 1 will send the update saying that 10.10.10.10 is mapped to 55, and leaf 4 will do the same for the mapping of the 20.20.20.20 to 56. Now, what we are going to do, so now we know that the source is mapped to 55 and the destination is mapped to 56. We are going to configure the contract, so we are not showing them on the slides because we will be checking the configuration a bit later, but we are basically configuring what we mentioned into the previous slide with all the columns and all the constructs. We are saying that from 55 to 56, we are redirecting to the firewall and to the IDS. So actually behind this arrow, we have this thing. So, okay, leaf 1 will apply the policy and redirect to the next hop. Obviously, it knows where the firewall is located because leaf 2 has announced the endpoint for the firewall thanks to a classic route type 2 update. So leaf 1 knows that the firewall is behind leaf 2. So it will send the traffic to leaf 2, and inside the VXLAN header, where in the field where we encode the source group tag, we will position 55. So this leaf 2, will receive the traffic with the tag being 55. And by the way, the policy applied bits that we have seen into the presentation of the VXLAN with GPP option with group-based policy, the policy will be 0. So even though leaf 1 has applied the policy, it has understood that for the traffic from 55 to 56, it needs to redirect it to leaf 2, to the firewall. It will send it to leaf 2. So it has applied the policy, but still it's putting A equals 0 so that leaf 2 understand that it needs to apply as well a policy. So on leaf 2, it will check again the policy 55 to 56, and it will send it to the firewall. So this is this arrow. And when coming back from the firewall, we are going to match on this specific interface and put all the traffic from the data plane inside the layer 4, layer 7 ESG that we have learned in the minutes before. So let's say that this ESG is 200, okay? So now, now when the traffic is being sent through the fabric, the source tag is now 200. And actually, Leaf 2 will be considering another entry into its policy configuration. Now it is saying, it's no longer saying what contract corresponds to the traffic from 55 to 56. Now it is considering the contract for the traffic from 200 to 56. By the way, right after, I have another slides which break down a bit the details behind the contract. Because in a future video, we are going to go to a lab environment and illustrate this with some show commands, and we are going to see exactly how it looks like from the perspective of the CLI and the returns from the switch. But still, in the next slide, I have a version that is oversimplified that shows how the different contracts are built. Because actually what happens is that when we configure the contract to say, okay, from 55 to 56, cross these two devices, what the switch will do in the background is break this thing into small pieces to say that, okay, from 55 to 56, it is actually 55 to the firewall. Then we come back to the firewall thanks to 200. Now it becomes 200 to 56. So now in the VXLAN header, the SGT becomes 200. And the last step is that we are going to cross Leaf 3 and reapply the policy, send it to the to the IDS. When we come back from this interface, we are being positioned into the layer 4, layer 7 ESG for the IDS, which has a tag of 300. And now the contract that we are considering becomes a contract from 300 to 56. And this time the contract is simply a permit. So again, I guess now you start understanding how all the pieces of the puzzle fit together. In the VXLAN header, in the SGT field, now the tag is 300. So we swapped it 2 times. In the beginning, it was 55, then it became 200, then it became 300. And finally, and finally, when it reaches the Leaf 4, we are saying, okay, from 300 to 56, just permits the traffic. And here, actually, the A bit will be 1. So the A bit will be 1 set up by Leaf 3, so that Leaf 4 just knows that it can forward. So this is the global idea of swapping the ESGs all along the journey of the traffic across the fabric. So just to show you what the configuration looks like for the layer 4, layer 7 perspective, maybe I should have put this one a bit earlier in the presentation, but never mind. So we are just saying configure security group. We give the tag as a classic ESG. We give the name, but here we are saying, okay, it's type layer 4, layer 7, and we are matching the interface. So this is a very straightforward configuration, but it's still, again, different from the perspective of how we are matching, because here the difference is that we are classifying into the data plane, while in classic ESGs we are classifying when learning by the control plane. And this slide is simply to remind that the policy applied bit can be set either to 0 or to 1 to say that we want to reinforce a policy later in the forwarding of the traffic. So just to summarize everything and put some perspective, if we come back to the slide, oh, okay, I should have cleared everything. If we come back to this slide, let me just quickly clear the mess and take back the pen. Okay. So now if you put all the pieces of the puzzle together and we consider our traffic redirection from 55 to 56, to which we were referring a bit earlier, We were saying that 55 to 56, we want to redirect to a firewall, then redirect to an IDS. This is all we need to say into our configuration. In the background, we have seen that the switch is creating multiple entries, so multiple, let's say, quote unquote, subcontracts to say, first redirect. So it will be explicitly displayed when we do some show commands that we have an entry with the redirect keyword and we have some entries with the permit keyword. So it will break this configuration into multiple small elements, and it will say whether we still need to redirect or we can simply go ahead and permit. So as long as we still have things to redirect, meaning as long as we did not reach the last hop, we will have the policy, we will have things programmed with the redirect, so the policy applied bit will be set to 0. So in the header, we will say, okay, please reapply something. And for the last stuff, when we send the traffic to the destination, it will be programmed just with the permit role. And this is what we are trying to illustrate into this specific slide. And by the way, let me just remove my head. Okay. So let's see what we are considering. So here we have our fabric with 3 leaves. So it's a bit simplified compared to the previous slide. And we have just one service with one service endpoint being the firewall. We have just one VRF named V1, not being very creative this time. And we have 2 classic ESGs, one ESG named client and one ESG named server. In the configuration, we are going to match on connected subnets on 10.10. Actually, it is 0 here, /24, to put them into the tag 55, and the same here, 0/24, to put them into the tag 56, which corresponds to the ESG server. So all this we have checked 1,000 times, and I believe we are clear on that. The firewall, we are considering that it is a 2-arm firewall. If it was a 1-arm firewall, it would be exactly the same stuff. Into the lab environment, we are going to consider only 1-arm firewalls. It really doesn't matter. What matters is that we do the proper configuration to say which interface is going to end up in which layer 4, layer 7 ESG. So this first leg, we are going to say that this is the firewall in ESG, and the second leg here is going to be the firewall out ESG. So the firewall in ESG, it has a tag of 100, and the firewall out ESG, it has a tag of 200. Here we are matching on interface VLAN 10, and here we are matching on interface VLAN 11. Long story short, I think you got it. What we want to do is ensure that 55 to 56 goes through the firewall. So we are going to go to the firewall in leg, come back through the firewall out leg, then go to the leaf 3, and for the return, we are going to go to the leaf 2, go to the firewall out leg, then firewall in leg, and then come back to leaf 1. And when I was mentioning previously that when we configure just this contract, what the leaf will do will actually break it into multiple lines, it's actually what we are seeing here. So we will have exactly the same subcontracts. It's not an official term, right? It's just to visualize the stuff. The same subcontracts configured on all the leaves. So the only thing that will differ is that we can have different rule numbers. It really doesn't matter, because what matters is the priority, but we are not going to see the details of priorities for now, really. We added this column just to mention that, okay, the rules can have different numbers. We don't care. So the rules are per VRF. We are mentioning the source tag and the destination tag. Here, the flow table is just to mention that we are going, this is for the forward traffic. And actually, it's, I forgot the, sorry, tilde here, to say it is for the reverse traffic. Okay, I have it there. I'm not sure. Okay, this is a typo, sorry. This is for the return traffic. But this is just an information to say, okay, the first 2 lines, we are considering them for the forward traffic, and the last lines we are considering from the return traffic. And the action, this is a very important stuff. This is where we are saying, okay, for this line, we are doing the PBR to firewall in, so to this leg. And when we do it and we generate the encapsulated traffic, the policy applied bit will be set to 0. And the other line is to say permit. And then when we have a permit, the policy applied bit is 1. So you can see that when we have PBR PA equals 0, when you have a permit, the PA is 1. I'm not going to enter into all the details of the lines because we are going to do this when we consider the flow of the traffic. So let's go for it. It's the last part of the video. So let me just again clean the mess, and we are going to dive into the forwarding of the traffic. Okay, so let's say that VM1 generates some traffic to reach the server. Obviously, this traffic will reach the leaf1. So what leaf1 will do, and I hope it's readable because it's a bit small. We are going to have a lot of information on this slide, so need to have small characters. So here we are going to say, okay, for this source class 55 to this destination class 56, we are going to check which rule is to be matched. So we have a rule that says explicitly from 55 to 56, do the PBR to firewall in. So leaf1 will say, okay, great, I have a redirection rule. So I will generate my VXLAN header with the proper fields and do the proper encapsulation and send it to leaf2. What does it mean, the proper encapsulation? So from the perspective of the inner IP addresses, obviously we are maintaining the original packet, which was this one. Then we say that the policy applied is 0 because it was a redirect rule. The source class, so the group, the source, the SGT actually, so the source group policy, it will be set to 55, which is obviously the group, the tag of the group to which belong the source. Then we code the L2VPN, which is for the VRF1. And the outer IP address, it is the loopback1 IP address of the first VTEP, and the destination, it is the loopback1 of the second VTEP. Nothing fancy about it. Okay, so the traffic is received by the spine, which routes it and sends it to the leaf2. So leaf2, it reads the packet. It sees that the source class is 55. It retrieves the destination of the, the destination group tag of the destination IP address. It checks its IP address entries and see that it is 56. Again, it knows that because leaf2 has, when it learns 56, it sends an update with that mapping. We are not going to say this 1,000 times into this video. Okay, so it checks this, and it checks what entry does he have, because it sees that the policy applied is 0. Since the policy applied is 0, it needs to check again the contract. So it will reapply the policy. Okay, it's looking for a policy for 55 to 56. It say, good, I have an entry for this. It is PBR to the firewall in leg. So good, it will send the traffic through the first leg of the firewall. The firewall will receive it. It will do the filtering. It will say, okay, that's a good flow. I will allow it. So the traffic is then sent back from the firewall to the leaf2. It will arrive on the VLAN interface 11. And now, because we have this match interface VLAN 11 in the configuration of the layer 4, layer 7 ESG, now we are classifying into the data plane, and we are saying that, okay, this traffic that we are receiving back will be sent, actually will be quote unquote mapped to the tag 200. So when we read the S class from that SVI, which is SVI 11, we are going to match it to the traffic to the tag 200. So now we are going to check again the policy, and this time the policy that we will be checking is the policy saying from 200, this time no longer from 55, this time from 200 to 56. What is the policy that we need to apply? And this time it is a permit. So, okay, since it is a permit, you are simply going to say the policy applied is 1. So the traffic will go from leaf2 to leaf3. Because we know, obviously, where VM2 is located, we know that it is behind leaf3. We are going to recreate the proper encapsulation. Inner IP address, inner source and destination IP address, they never change. The policy applied attributes this time is 1. The class, it is 200, so the one of the firewall out interface. Sorry, let me again remove my face. Okay. And we have the L2VPN and the source and destination of the outer IP of the outer IP header being the VTAP IP addresses of leaf2 as a source and leaf3 as a destination. So leaf3 will receive this, and it sees that the policy applied attribute is actually 1, so it doesn't need to do anything, and it will simply forward the traffic to VM2. By the way, even if in any case we have the contract that say, okay, for 200 to 56 it is a permit. It is present on all the leaves because it's just symmetry of configuration. But here actually we don't even need it because the policy applied attribute is 1. So we just need to do like if it was classic forwarding. So we are just doing some classic routing. So this recaps how the forward traffic looks like. And I think that now it should be clear for everyone how it happens. But, you know, just for the sake of completeness, let's see. Sorry, I forgot to show this, but yeah, this is what we have in the end. We have the 200 to 56, we have the PA being 1, so we are going to bypass and forward to the destination. So let's see now what the return traffic looks like. So this time we are considering the source IP address being 2020, and the destination is 4 times 10. Okay, so the leaf3 receives this traffic. It will retrieve from its learning the class of the source and the class for the destination. So this time we are considering traffic from 56 to 55. So for this traffic, we are going to go to the firewall out first, then to the firewall in leg. Okay, so leaf3 will say, okay, I have traffic from 56 to 55. Let me check in my configuration, in my entries, if I have a contract for that. And it finds it. So it is the contract for the return flow, which is matched by the small tilde here. So contract from 56 to 55, go ahead and redirect to the PBR. Go ahead and do PBR to firewall out. And obviously, since it's a redirect, the policy applied bit is set to 0. Good, we are going to create our header and our encapsulation. So inner IP addresses don't change. The source class, it is 56. PA equals 0. Let me go a bit faster this time. The traffic is forwarded by the spines and reach 2. So leaf2 reads the source class being 56. It retrieves from the learning that the destination, so 4 times 10 has a destination class of 55, and it also sees that PA is equal 0. So it means it needs to check again in its entries for a contract from 56 to 55. So it's checked the contracts and it finds a line saying from 56 to 55, redirect to the outer leg of the firewall. So it will go there. The firewall will permit it, and the traffic will eventually comes back through the firewall in leg of the firewall. Okay, so this time we are coming back. Sorry, I forgot to. So we are going through the interface 11 and coming back through the interface 10. When we come back from the interface 10, this time we are put into the ESG that has the tag of 100. And again, a new lookup into our entries for our contracts. So we are going to check from 100 to 55. What do we have? We have a permit. So we are simply going to create, again, a new VXLAN encapsulation header with all the required information. The source class this time is 100. So this one from the return traffic. And the PA is 1, so that's the leaf1. When it receives the traffic, it knows that it doesn't need to apply anything, so it just needs to permit the traffic towards the destination thanks to classic routing. Which brings us to the end of this presentation. Okay, I see that the video is almost 2 hours. I think it's the longest video I did. Yeah, really, I hope it was not too long and it was not confusing. Really, I wish it was useful. Yeah, in any case, it's never easy when we learn a new stuff. So we need to, again, like I like to say, it takes some time to understand how the pieces of the puzzle fit together. But eventually, and hopefully, it gets clearer with practice. And speaking about practice, this is what we are going to do. in the next video. So we are going to go to a lab environment and check in details the configuration, apply it, and see together how everything works in a not a real environment because it is lab, but on physical boxes, right? On happy living Nexus 9Ks. So thank you very much for your time and see you in the next video. Please take care.